Let's look at voltaic cells and how their line notation tells you the reaction overall. So in the reaction, in the line notation, there are two half reactions, and there's one on each side. So this is a half reaction, and so this is lead reactant and lead product. And then on the other side, we also have another half reaction where we have the silver ion reactant and the silver solid product. And that's one thing it doesn't always show you, that when you don't have the charge, it's understood to be a solid, and when you do have the charge, it's understood to be aqueous. So our lead in this reaction is going from lead neutral to lead with a charge, and that means that it is losing electrons. So I'm going to put the electrons there, and actually I can tell because it goes from neutral to +2, it must be having 2 electrons being lost. This is our anode, and on the line notation, the anode is always on the left, and that is always where oxidation takes place, which this is. Loss of electrons is oxidation. If we go to the other side, we have silver with a charge going to silver that is neutral, and I left some space because I know it must be gaining an electron, and so this reaction is the cathode, and it is reduction. So those things always go together. On the right, it's always the cathode, it's always reduction, it's always accepting electrons. So if we want to write a complete reaction, we need to see how to put these together. And maybe you can do that just by looking at the number of electrons involved. But let me kind of just go through the steps of how to do that. So I have each half reaction. And then I can see that I don't have the same number of electrons in both cases. So I see that I'm going to need 2 of this bottom one to go so that we have all the electrons balanced. In other words, so that lead is giving off the same number of electrons that silver is taking up. So I'm just going to double this bottom one. And then I could think of it as adding these two to get my net reaction. So I'm adding all of my reactants here. And I'm going to go ahead and put back those states. And notice that I did not write the electrons because we can think of them as canceling here. So this reaction is our complete reaction. When it asks you to write a complete one, you have to figure out, what's going on with the electrons. And then just a note, we'll be using this later. There were 2 electrons being transferred in this, and so later on we'll use that for N. N is the number of electrons being transferred. Okay, and then we're going to be calculating some cell potentials. And to get a cell potential, we have to consider the 2 different types. In general, cell potential, is just however much usable energy something has, and this would just be what you observe in the lab, or you could calculate it and make a prediction. But the thing is, that's for whatever conditions that you have. When you use the tables are at standard conditions. And so when you see this little degree sign here, that means standard conditions. And so This would be the cell potential. And the standard conditions are basically the solutions are at 1 molar, 25 degrees C, which of course is 298 K, which we will be using. If you have a gas, it's 1 atmosphere. We won't see that on this. But anyway, so when you use the tables to get the cell potentials or the half cell potentials, those are under these conditions. And if you're working at different conditions, like we're going to see different concentrations, then you can make a prediction based on that change. Let's look at the table. So let's look at our table of potentials. And so these are the half cell potentials based on reduction. And it's labeled, but also I can tell that these reactions are reduction reactions. They're gaining electrons. So these potentials are for the reaction occurring at the cathode. So let's go back and look at our, well, this is actually a different one, isn't it? So on this line notation on the left, of course, this is the anode, and that's oxidation. Okay, so it appears that reaction is not here, but there is a way. On this reaction, again, on the right, we have the cathode, and this is reduction. So that's convenient. This one is there. So that is the half cell potential for our cathode. Okay. If we want our cell potential overall, though, we need both. So we have it for the cathode. And do use the number of sig figs that they give you on their charts. But then to get it for the anode, I need to know what to do. So what I do is I take this number, and since that number is for reduction, and I need, this is oxidation at the anode, I change the sign. So the cell potential overall that we've made is 1.100 volts. Okay. And because I used that table that had standard values, this is under standard conditions. That's what I would expect for the voltage. Well, what if the conditions are not standard? Then we use the Nernst equation, and this has different forms, but this is the one that they give you. So on this, I don't know if they tell you that so I gave you the R to use. It's the gas constant, but it's the one in joules per K moles. And do use 4 sig figs because they give you 4 sig figs and everything. Also, I don't think they tell you what temperature to use, or maybe they did, but basically we're going to use the standard temperature, which is 298 Kelvin. And N is the number of electrons transferred in the complete reaction. So remember when I marked up above, when we wrote the complete reaction, I told you that N was 2 because 2 electrons were transferred. And then we have the Faraday constant, and then Q. Q is like QC, so it's kind of like an equilibrium constant. It's products over reactants. Okay, so let's look at an example. Okay, in this example, I can tell that it's not standard conditions because my concentrations are not both 1 molar. The zinc is, but not the copper. And so just kind of keeping track of that. First, I'm going to calculate the QC, my reaction quotient. And remember that when you write one of those, so I've written my equation here, you have to kind of watch. It's easy to get things in the wrong order because you have to remember this is a product and this is a reactant. So things are kind of, they look opposite than what you're used to. But anyway, so I wrote my reaction, and then like I would normally do for my equilibrium constant, I ignore solids. I would put my zinc solution on top, and it's no coefficient, and then I would put my reactant underneath, like so. That's how I would do my equilibrium constant. So basically my QC is the same thing, just with the starting concentrations. So I'm going to put my zinc on top, divided by my copper. And I get 10. Now I'm going to plug into this equation. So this is the one where I calculated using the table, was the standard one. Okay, and remember this N was the number of electrons. When you do this calculation, these other 3 numbers are the same on all of them that we're doing, so you could just punch them out once and then you kind of know. But anyway, and then this was my Q that I determined above. And that's it. So that is my predicted cell potential on those conditions. I know that they give you like an observed one, and it should be close to that, but it won't be exactly that.